Hey folks, this is AP Chemistry, and you're here with Miss Gray. We're in Unit 8, which was all about intermolecular forces, IMFs. In our previous podcast, we've talked about how IMFs would influence the properties of liquids. So now let's investigate a little bit the forms and properties of solids. First of all, one kind of structure for a solid is a crystalline structure. For a solid to be crystalline, then the particles it's made of, whether it be atoms, ions, or molecules, would be ordered in well-defined arrangements. In other words, they have regular repeating patterns that we can predict and calculate. So they would have flat surfaces or faces, definite angles, and regular shapes. So they have a structure to them. An amorphous solid is a solid whose particles would have no orderly structure, with a lack of the well-defined faces and shapes. And so generally these are made up of mixtures of molecules that just don't stack very well together. So they're composed of large, complicated molecules that don't have a pattern to their arrangement. Crystalline solids then tend to melt at a definite temperature. They have a melting point that we can describe and tell everybody else about, right? But an amorphous solid would soften over a wide range of temperatures, and so it's harder to predict the melting point of an amorphous solid. So think about like wax or glass. Those are examples of amorphous solids that soften before they actually truly melt. So now let's look at metallic bonds. Metallic bonds are a special type of structure for solids in that a positively charged nucleus would have an attraction for an electron, but the electrons are not bound to any particular nucleus. They're free to move about throughout the entire matrix of solid nuclei because they would experience an equal attraction for any of the positively charged nuclei. So we call these mobile electrons, and that determines the properties of metals in being very conductive for heat and electricity, and also that they're easily malleable. We can bend them and stretch them into wires because they're ductile. So metallic bonds lend a lot of unique properties to metals that other elements don't have. So let's look at alloys then. An interstitial alloy, like steel, would be one where there are smaller atoms that fit into the holes between the solvent metal atoms. So suppose that these are iron. One common atom to add to steel is carbon. Then we call it anodized steel, basically. And it adds a lot of strength. And the higher the percentage of carbon in the steel, the stronger it's going to be. Another type of alloy is called a substitutional alloy, and this is usually created when the two particle sizes are very similar. And a substitutional alloy is one in which atoms of the solvent metal are actually replaced with atoms of the solute metal. And so one example of that is brass. In brass, we would have mainly copper atoms, and then some of the copper atoms get replaced with zinc. So that's how we would make brass. Remember the penny lab that you made gold pennies last year? That was when you made a substitutional alloy, adding zinc into the actual atomic structure or atomic arrangement of the copper atoms in your penny. So there are a couple of different bonding models for metals. In one model, we would have the electron C. And in the other model, it's the molecular orbital model. But basically, it all has to do with our electrons being free to move around throughout the metal crystal in molecular orbitals, according to the molecular orbital theory, or as a sea of electrons in the electron C model. Those are the bonding models for metals that you should be aware of. And I think that's it for solids. Oh, no, we have one more. Something that's even stronger than metals would be our network solids. Typically, we call these covalent network solids. And so when we have a whole bunch of covalent bonds that are all in a network together so that it looks like a giant molecule. So there's no place to say where it begins or where it ends because it just is all stuck together in the same regular repeating pattern. Then that's when we get a covalent network solid. Diamond is one of those that it's known for its strength. Ceramics and glass is another, where we would take silicate-based molecules and bind them together in a very rigid structure so that it adds a lot of strength, especially the links in the intermolecular forces basically all become intramolecular forces here because all of the particles bond together in one large network. So this results in very high melting points. In fact, when steel is being manufactured, they rely on the high melting point of ceramics to be able to contain molten steel. So that's what we need to know about solids and IMFs. Guess I'll see you guys in class.